Hi, everyone. I forgot to unmute it. Arthur gave me a nice introduction. Right. Given a diverse interest in the group of some emissions and some chemistry and a number of excellent analytical chemists, I'm trying to sort of dabble in a few different storylines today. So lots of co-authors that are involved in the number of papers that are being presented here, and need to. Right. Oh, I know it was on that. All right. So a number of different funding agencies contributed to some of the work that we're showing. We have a couple of different big field sites, and also want to thank my research group, which includes a lot of really awesome undergraduates that got to contribute some of the research I'm showing today. And so we'll structure this in a way where I'll talk about a few papers quickly and some of the sort of underlying themes in the group, and then talk about two different papers that came out, one focusing more on emissions, and another looking a little bit more at atmospheric complex mixtures and organic aerosol. So my group does a lot of work on emissions, organic processes, and new toys in the lab. Just as a very quick refresher, we have a really wide variety of sources in the atmosphere with different emissions rates and composition, and they give us a mix of gas phase organic compounds, and it's going to vary depending on the exact source, both in the composition and rate. There will be some primary organic aerosol emissions, but then through multiple generations of oxidation chemistry with a variety of oxidants, we're going to get SOA formation and growth, as well as some highly oxidized gas phase products and a variety of reactive other species and ozone. So we won't dwell on that too long, so I think everyone here knows that pretty well, but I'll talk a lot about the volatility basis set spectrum today. And so we know VOCs very well, and then IVOCs, SVOCs, and lower volatility things represent an important group of organic compounds that are historically less studied. And of course, vapor pressure is highest over here, most here. And so, but are very important for SOA formation and are very interesting in terms of their behaviors when it comes to emissions and their dynamics, both outdoors and indoors. All right, so on to some things from my research group. To generate future discussions, just going to have a couple slides here talking about some new instruments. So we have an EPA research center with Johns Hopkins. I have a project in that center where we've designed both a stationary multi-pollutant monitor as well as a portable monitor. You can see it's here on the shoulder, right in the breathing zone. In all of these, we're measuring size result PM, CO, CO2, ozone, NO, NO2, and methane. So a multi-pollutant suite, both criteria and climate pollutants. We have a network of stationary monitors spread across Baltimore. And then within that high-density network, we have personal monitors on participants who are sort of going about their normal lives. So we're looking at both stationary and portable network that are superimposed upon each other. And so this is happening as we speak, and these monitors are in Baltimore, and we get to see some really interesting spatial temporal dynamics. But we'll have to wait another day to talk more about that. In other cost-effective instrumentation, we had a paper in January in analytical chemistry where we were able to use vacuum GC with air to generate chromatograms that provided the same quality of data as GC FID. And so this relieves you of the need for gas cylinders. You can do very good chromatography with it, and actually we were able to get down to detection limits 1 to 10 ppt range, and see a lot of functionalized things coming through, including things in the IVOC range. So this was a really fun analytical problem to work on. So I encourage you to go check out the paper, and I'm happy to talk about it more afterwards. I would happily give a whole talk on this, but I'm afraid by the end of it, I would have about half of the room left here because everyone else would be sick of me talking about separations and diffusivities inside GC columns. So, so a couple of things that I'll be presenting today will relate to our ability to characterize complex mixtures of organic compounds. We do work with both GC and LC, as well as collecting samples on gas phase adsorbent tubes that we design and build ourselves in our lab, as well as particle phase samples on filters. So there's a great paper out in 2018 on our adsorbent tubes by Roger Shu et al. Talks about how we were able to get to these really low detection limits with them. And then there's a paper, Kare et al. From 2019 showing their applications to complex mixtures. I'll be talking more today in the second half about our use of liquid chromatography with self-ionization electrospray. But using these gas phase adsorbent tubes, we're able to get speciation across the IVOC and SVOC range, and including some ambient unresolved complex mixtures that are made up of a variety of functionalized species. So soft ionization, as a quick reminder, allows you to preserve the molecular ion rather than getting fragments. So by preserving that molecular ion, you're able to look at that whole mixture and see each molecule that exists. And so here is some work that we've done on oil sands in collaboration with Environment Canada. And so each of these carbon bubbles is a mix of hundreds, if not 1,000 isomers at a given carbon number, and they change based on their molecular structures. So we're able to, in this kind of targeted analysis here, use these really high accuracy masses to sort of precisely dive in and look at all the different compounds that occur on a molecular formula, and as opposed to an unresolved complex mixture, which is what this looks like if you run it on a sort of old school electrospray, or excuse me, electron ionization mass spec. So taking this kind of plot and then integrating for each molecular formula, you can actually look at the breakdown as a function of carbon number and molecular formula. Here being your linear and branched alkanes, and then going up to monocyclic, bicyclic, tricyclic, and then getting into your single ring aromatic, your pHs. So we've also been able to apply this for functionalized mixtures, and so we see for things containing one oxygen atom or sulfur, and nitrogen, multiple oxygens. And so we've seen these things both in emissions as well as in the ambient atmosphere. So it allows us to sort of pierce through a complex mixture that might otherwise be obscured by all the other hydrocarbons in it. You can actually look at the functionalization and look at the amount of sulfur or nitrogen that might be coming from that source as part of its sort of complex mixture of precursors. All right, so please follow up with me more if you want to talk about any of the instrument things that I showed there. But now I'm going to jump into the first part of our story, which is looking at non-traditional emissions and or non-combustion emissions, or what has also become volatile chemical products. So the general story here is that Arthur mentioned that I'd done a lot of work on motor vehicle emissions, and which was really interesting, but something jumped out at me as I was working on a review paper in 2017 for that, and that was there's all these other sources that are not being controlled as effectively. And so we'll come back to a comparison of those in a moment, but if we look at what we know about for sort of non-traditional emissions as they're reported, we have a mix of things you would think of: paints, pesticides, cleaning products, but then we get into a whole number of other things here. The ones that are starred are not in current emissions inventories: furnishings, building materials, asphalts. They don't get a star because they're included, although extremely poorly, and then solid consumer products. And so the world of these non-traditional emissions are the things that we really haven't focused on much, and especially not in the last 30 years, are playing a bigger role in air quality. And so to make this case, I want to show you motor vehicle emissions and how they changed over 5-year increments. So if we look at 1990 here, and we have vehicle population, fuel use, and VOC emissions. And if we focus on the left side, as we're shifting to 95, 2000, 2005, our vehicle fleet is shifting from pre-low emissions vehicles in the US into low emission phase 1, phase 2, and phase 3. And so you see over time we shift to the newer, cleaner vehicles. We're still consuming a lot of fuel, so there's smaller changes there. But now look at the VOC emissions here. You went from having all the VOC emissions coming from pre-low emission vehicles, and then as you transition into the newer vehicles, you don't have as much. So this is an amazing success story. It had a huge effect on primary pollutants in a number of urban areas. It had an effect on SOA formation for sure in places like Los Angeles. And so if we look at how these emissions changed here over 1975 to 2020, and this is just what's reported in the emission inventories in their current state. We have the fraction of emissions shown here as the traces, and then the overall total anthropogenic emissions shown here in the bars. And so you see this sharp decrease, and what's driving that is this here, the decrease in on-road motor vehicle. And so at that same point in time, all of these non-traditional sources labeled here in green, and just the reported ones again, are playing an increasing role in the spectrum of all of the reactive VOCs in the atmosphere. And so we used this data and looked at the SOA and ozone formation, and we see that their effect on SOA and ozone in these areas is also, or their relative contribution to SOA and ozone is increasing. And so here we look at gasoline and diesel vehicles. So gasoline shown in red and diesel in blue. And if we look at SOA, we see this very sharp decrease from the decrease in aromatic emissions coming from gasoline vehicles. And we have this less regular, we had some very early regulations on consumer products that sort of stopped around 95. And so we see this sort of just staying flat. And so the decrease in gasoline diesel vehicle SOA means that now, at current day, both in total emissions as well as potential SOA, non-traditional sources that include consumer products and all these other consumer and industrial products are actually dominating VOC emissions, which has some important implications because it means that we need to think about a broader context of sources, and we need to advance our state of knowledge on those sources and understand the emissions coming from each of them and how to control them and what to replace. So we see a similar story occurring with ozone, although the point at which we hit equilibrium between the non-traditional sources and gasoline is a little bit later in this analysis. So, and again, this is just what is reported in the inventory. And so we did a thorough analysis of the inventory, a number of other sources, and looked at products, and there's definitely some clear gaps that need to be filled in. So sticking with what is currently reported, here's a spectrum of all the things that are emitted in the Los Angeles area, just as a function of compound class. So you see some things that you're sort of used to thinking about in terms of their chemistry, both for SOA and ozone formation and other urban and indoor chemistry, but then we get into some different things that we really hadn't been thinking about as much. And then we have a whole bunch of things that are just miscellaneous or really poorly speciated IVOCs and SVOCs. And I'll go on to make the argument that what we estimate as this is probably much larger because our reporting for these lower volatility IVOCs and SVOCs is very dated. So if we break this down as a function of what sources it's coming from in terms of consumer products in the current inventory, we see an outsized role for paints here, although this desperately needs to be updated because we looked at a number of high-selling commercial paints and consumer paints and do not see a lot of things that are reported in there. And then looking at different consumer adhesives, industrial adhesives, pesticides, sealants, and cleaners, you see a breakdown across all these other functional groups. So I won't go through this in more detail, but if you look at the paper, you can see all the numbers. So, all right, we did an analysis of a variety of products in our lab to compare to what was currently out there in the inventories and also to compare what was in the MSDSs, the materials safety data sheets. And so if we look at this figure here where we have these different products that we tested in our lab, we did a couple things. First, we looked at the total emittable fraction shown here in green. So what fraction of that product as a liquid was going to be emitted if you applied it over a reasonable time scale. And so that pretty much means everything that would be in the VOC or IVOC range here. And so you can see some of these have a larger fraction of non-volatile or extremely low volatility things, and a number of them will get emitted at about 100%. Then the other thing we did was speciate them to look at their IVOC and aromatic content, shown in red and blue here. And so in blue is their IVOC content. You see in the case of the insecticide, about 95% of it was IVOCs, and then we get over to some of these other products, and we have a healthy fraction of anywhere from 1 to 3%. And in the case of aromatics, which we also know to be very important for SOA, we looked at their prominence in all these products, and we do see a couple products that have really high aromatic content. Those may no longer be things that are including toluene necessarily, although some of them do, but it could be some newer aromatic species that are put in to replace them. And then a number of products that have small aromatic content in them that if you look at the total sum of those, because remember, these are going to be emitted at 100%. We're not putting them in an engine where we're going to burn the vast majority of it. Everything that evaporates makes it into the air. The interesting takeaway there is that many of these still contain considerable aromatic content, despite that being one of the things that we targeted with some of our early regulations in early 1990s. We see significant IVOC content, and in many cases, those aren't always disclosed or readily available with information in inventories. And the last thing here, we took these products and went and did testing looking at their isotopic content. And the fascinating thing that we found is that the carbon-14 testing shows that pretty much all of these are primarily from fossil fuel feedstock, which is not surprising, but everything, so many of the materials, chemicals that we use in our lives all come from fossil fuels as their precursors. So the interesting thing about that is that these studies that we're looking at the isotopic content of aerosols, especially in California, when Arthur and I were there and during CalNex, all were looking at the SOA. And they said, we see this massive fraction, and it's all fossil. And so what was said is fossil, well, that means combustion, which means it's probably motor vehicles. But we tricked ourselves because we had all of these precursors that appeared to be fossil because their feedstocks were, but they weren't actually involved in combustion. And so the fact that we're able to show here that these things have primarily fossil backbones in them in terms of their isotopic content means that we can now interpret those results a little bit better to see that the SOA we're looking at wasn't all combustion and from motor vehicles. A large fraction of it actually was coming from different consumer and commercial products. So we did a survey of the material safety database for 50 in each of these categories, high volume sales products from readily available providers to look at currently what is the aromatic and IVOC content. So we're showing here the fraction of products that contain aromatic content still and the fraction that contain I and SVOC content. And you can see that a lot of them do have these very reactive SOA precursors in them. And the interesting thing with some of the I and SVOC things is how that still isn't the full scale of what's actually in there. That's just what is reported. The content varies widely as reported in the MSDSs because there's lots of things you're able to get away with by saying you're protecting commercial information, the rules of disclosure, and there's a whole bunch of compounds that are technically not VOCs. You can go buy, I'm not telling you to do this, please don't do this, a 100% terpene additive for your paints. It's an air freshener that will effuse from your walls for months at a time. It is 100% terpenes. On the packaging, the website, the MSDS, it says 100% VOC free. No VOCs, amazing, right? But it is literally limonene and all your other favorite terpenes that are just oozing out of your walls, which obviously presents interesting implications, not just for urban emissions, but also for indoor chemistry. So the MSDSs were a really interesting exercise and allowed us to constrain the relative use of aromatics and INS VOCs in some of the current products, but it has lots of gaps. By far, one of the most dramatic was pesticides that I leave up here sort of just to prove a point about how poorly they're disclosed. And pesticides from a number of our tests we see a lot of INS VOC content in them. So there's tons of uncertainties throughout this whole thing and a lot of knowledge gaps that have to be filled in. So looking a little bit more at the INS VOCs as part of this paper and to show their prevalence, we looked at a number of different, we did 2 case studies in there. One looked at pesticides, and so here we're showing a couple different ones that we analyzed, and we see some IVOCs here on these 2 insecticides. And then at the same point in time, we analyzed horticultural oils, so things that are especially used in sort of industrial agriculture. You can even buy these things that are organic because it's just a mix of aliphatic species. And see a really large concentration here of different semi-volatile organics and a number of IVOCs. So I don't have to tell everyone in this room that if you go and put this all over surfaces outdoors, you've just created a very nice emission source that will slowly come to equilibrium and continue to contribute reactive IVOCs and SVOCs that can lead to SOA formation. Second, we looked at the sort of current understanding of asphalt-related products and processes because we use a lot of asphalt. And emission inventories only include solvent emissions, which is only used in a few exceptional cases now. But what it doesn't include is all the degradation byproducts, because asphalts are non-distillables. They come from the bottom of the column after you've even done vacuum distillation. It has no VOC, IVOC, SVOC content in it by definition. But you start cooking it and heating it for transport, application, all these things, you start seeing a lot of emissions from it, of VOCs, IVOCs, and SVOCs. Anyone who's at the Gordon Research Conference, you can get a sneak preview on a paper we're working on related to that, my graduate student, Piyush Khare. So this effect is known from the public health literature because of all the OSHA studies of construction workers applying asphalt. But beyond that, the connection wasn't made that this was actually an emission source. And the thing that I really like about this as a case study is it points to the importance of not just the things that we know we put into products and materials, but the things that can form from them. So, and especially low volatility things. And so the INS VOCs represent key SOA precursors, but they're severely represented in existing inventories. And one of the really interesting things is that our data is currently focused on more rapid volatilization, so things that are occurring shortly after our product is applied or used. We're not thinking the long game here. And so if we look at that long game, here as a function of carbon number, we're looking at emissions timescales. And so we have a range of VOCs, IVOCs, and SVOCs. Here in red, we're looking at the N-alkanes or the alkanes of equivalent volatility. And then we have some single ring aromatics over here and a few small oxygenated salts. So the left and right y-axes are the same. They're all emission timescales. Here, I'm giving it to you in hours. On the other side here in days with some marks for different years. So a lot of these small VOCs, and this is for, I should say, a thin layer of an applied material or something that's been coated. And then we're looking at the vertical transport velocities that would be typical in outdoor environments. If you were translating this to indoors, your vertical transport velocity is actually lower. So these timescales will become longer. And so, all right, if we follow this here and look at, about 1 hour, here we are sort of at the boundary of VOC and IVOC. And here's this, the dashed lines are looking at different sort of uncertainty ranges in terms of the vertical transport velocity as well as the thickness of the coated material. So, right here, that puts you at about an hour to emit, to get to 1 E-folding of the total amount of initial content that you have in your reservoir. But if you start to go up in more IVOCs, you quickly get to a day here, then to several days and into months, and then here in the SVOC range, you can hit a year. So this points, and then you could keep going with this, but this points to the potential that we have this incredibly large reservoir of emissions that exist both maybe in the outdoor world, but also in the indoor world that can be affected by temperature, weather, and other factors. And got to talk and hear some really cool results from the Abbott group thinking about the same concept but applied indoors and looking at partitioning. And so I love that conversation, thinking about how we have this banked amount of emissions in these reservoirs that occur in indoor and outdoor spaces. And certainly the work that's been done here at U of T looking at emissions indoors and changes in concentration over time, and with outdoor ventilation, provides some nice connectivity here to the fact that we do have a really strong emission source indoors where we use these materials. So, and finally, we also looked at the SOA yields of all the different individual products that we analyzed, as well as their ozone formation potentials and the different average composition of the inventory product categories, the ones that I was showing earlier, and compare those to motor vehicles as well as commercial cooking. And we see a wide range here, but also that they fall in the same range for SOA per gram of precursor from motor vehicles. But remember, these emission factors are rapidly decreasing in these top three. Same thing for ozone formation potential, a range that competes with those other sources. All right, so a few key findings here to summarize. These sources are becoming increasingly important for air quality, especially with our successes in control of combustion sources. But really important, if you remember anything, that emissions aren't occurring just from the evaporation of solvents. That's the emission that you see and smell when you're cleaning your home. But in fact, you also have the solutes that are dissolved in these products and degradation products. And so we really have to be our best industrial ecologists and think about emissions over entire material life cycles. These emissions lead to greater potential SOA and ozone formation in our case study sitting in Los Angeles, and this is now work being done in other cities and seeing a similar pattern. And we just talked about the SOA yields and ozone formation potentials being the same. But really important is that there's a lot of good work that has to be done in validating and updating these emissions in inventories and understanding their source profiles, because we have a limited understanding at this point. And especially IVOCs and SVOCs that are poorly represented, but it represents substantial SOA formation categories. And then finally, we talked about the carbon isotope analysis shows that these things are going to masquerade as fossil emissions if we're looking at them in the SOA that's formed in the atmosphere. So in this paper, in my closing part about this paper, talk about the comprehensive framework that we put forward. One, think across the full range of volatility and research our emission inventories across that full range. Two, that we look at source categories that are highly diverse and include things we're already including, but also a lot of products and materials that we are not. Three, that we need to think about emission pathways with the same rigor that we did for motor vehicle emissions when we broke it up into tailpipe, evaporative, looking at vapor leaks, liquid leaks, and really breaking apart the motor vehicle in a mechanistic way. So here we can bring an engineering perspective and look at emissions that occur from evaporation of the solvent. So the very light things, the volatilization or off-gassing of a solute or active compounds in a material or applied coating, And then finally, the volatilization of byproducts from degradation or environmental stresses. And this could occur from even like a solid product or material, such as building furnishings. And finally, again, we need to bring our best life cycle analysis skills and account for emissions, not just at the time of application, but really thinking about the full lifetime across application, curing, use, and even all the way to removal and disposal for materials. So with that, I'll wrap up this sort of first story about this paper, but please do check it out, and feel free to follow up with further questions about it. There's really a lot of cool work that needs to be done in this area. So, all right, deep breath. On to the second part of the two-part feature. So if you weren't into emissions, hopefully this part of the presentation will suit you a little bit more, looking at complex mixtures of organic compounds in organic aerosol. So this paper was published back in the fall in 2018 by Gentner, a great graduate student. And I was actually really excited to find out recently it was an editor's pick from that year, and then also Jenna got an award from Desert Research Institute very recently for this paper. So the research question we were trying to answer is, how does the molecular level composition of functionalized organic aerosol vary temporally? So when I'm saying functionalized organic aerosol, I'm meaning anything that is like, has a CH backbone plus oxygen, sulfur, nitrogen. And so you could think of this broadly as secondary organic aerosol, although we do have primary emissions of functionalized species. And so we wanted to look at how the variability in this molecular level composition compared to bulk composition observations, so things like AMS. So over here we're showing some data from CalMax 2010. And you can see the diurnal plots here, and the change in O to C is actually pretty well constrained and also well behaved over the course of the day. It's pretty repeatable day in and day out. So this suggests you have a system that is just sort of stuck in a loop, doing the same thing over and over. And so we looked at a number of different field sites to look at the variability there, and then what drives the compositional variability. So we'll talk about methods and sites, jump into our results, look at temporal variability in this isomer-specific compositional analysis, and then do a comparison to chamber experiments as well as current chemically explicit models. So, all right, some more instrument details. We do, in one part of my lab, a lot of work with liquid chromatography and tandem mass spectrometry. So here I'm presenting things that were collected on filters in multi-hour samples. Were separated by LC and then soft ionization, and then identification of the molecular ion using a tandem mass spectrometer. So we're looking at 3 different field sites plus a chamber, and this mass spectrometer has a very high resolution as well as a very good mass accuracy, and we're pulling it apart using LC, which enhances our ability to speciate that mixture. We are not going to go through all the extensive QC/QA, so hopefully you can trust me on this, but we did a lot of work validating these results, looking at standards, looking at blanks, applying variable limit of detection thresholds, which I'll show you later, more sensitivity analyses than we have time to talk about, and then a lot of screening based on current best practices in the field for the results coming out of QTOF. If you're really interested, there is an extraordinarily long supplemental information section in this paper that has all of those details in it. But the one thing I want to remind you is that every compound I talk about today or show you is a unique LC peak that has a high accuracy formula assigned to it. So we do have both good LC information as well as mass spec info here. All right, so 3 different sites. The Profit site in northern Michigan, where we're up here at the top of the tall tower, just outside of downtown Atlanta, and then also in New York City in Queens. And then we also looked at chamber experiments from Sally Ng's group, and then worked with our collaborators at NCAR to run the Gecko-A model to look at the results. So, okay, to start off, if we look at the day-to-day elemental composition for any of these 3 sites, it's actually relatively consistent. So here we can look at Atlanta, and the total amount of compounds with carbon, hydrogen, and oxygen in the functionalized organic aerosol is about 50%, with a pretty, tight uncertainty there, standard deviation on there. And so the general chemical composition in terms of the elemental breakdown at this level is actually not changing wildly. And this also aligns with the AMS Odyssey measurements in Atlanta and the forest that show relatively limited variability across the course of these campaigns. But now when we take a dive further down and look at this at the molecular level, we actually see much greater level of variability at the molecular level. And so what I'm showing here is just a basic 3-sample comparison from the daytime of July 29th, the night, and then the following day on July 30th. These pie charts are the same thing as the bar charts on the last plot, where it's showing the breakdown of the different compound classes here. And then these bars, these pie charts in the middle are the fraction of distinct compounds versus overlapping compounds. So distinct is what's shown in the shaded parts of the pie charts. And so here, comparing daytime of July 29th to the following night, 50% of the compounds that were measured in those multi-hour samples were distinct from each other. And then when we compare that night to the next day, we see that 63% are distinct or unique in that sample-to-sample comparison. And then even when we say, okay, if it's just a sort of day versus night thing, comparing 2 sequential days back to each other shows 64% of the compounds at the molecular level in the organic aerosol are distinct. And so we repeat this for all of the samples. And so here I'm showing you the Atlanta, where we're comparing day to previous day, night to previous night, looking at the percentage of them that are distinct, as well as night to previous day and day to previous night. And we see this variability spread across all of them. And overall, we see that 40 to 95% of compounds in a given sample were distinct in comparison to a previous sample, the day or night before, and that this variability is equal between day and night. If we look at this across all 3 campaigns, we see that the molecular level variability is at about 2/3 between any consecutive samples at a given site. So 66% of the compounds in functionalized organic aerosol are actually changing from sample to sample, which suggests a much greater extent of variability than we would get from our bulk measurements. So if we look at the forest here and then Atlanta in the middle and New York City, if we're comparing all consecutive samples, you can see here we are at about 66%. And then we looked at all daytime samples and all consecutive days. And we see if we're just looking at consecutive days here in Atlanta, it agrees slightly better with previous samples than if we're doing all comparisons. We looked at nights as well as, again, all consecutive nights compared to all nights, and see less variability if you're just doing a consecutive comparison rather than all nights to each other. And then finally, days to nights, night to days. So we see a pretty consistent behavior across these 3 different sites, and that this repeats itself depending on we're comparing time of day, day versus night, or just day and night together. So, all right, we wanted to figure out where is this variability concentrated? Is it just a bunch of the really small concentration compounds? And the answer is no, but we do see more variability in the lowest quartile of concentration compounds. But we still see that 20% of this variability is occurring in the most dominant compounds of the mixture. So those at 75 are in the highest quartile. And so this is spread across the whole mixture. We looked at differences in terms of volatility, and the only significant thing is that LVOCs seem to be a little bit less variable than the others. And then we looked at the function of different compound classes, and again see that no singular compound class is driving this effect. So there's not one thing that's sort of being turned on and off that's driving it. So no single subgroup of compounds is dominating this variant. All right, you might be thinking this is a little bit isolated to maybe a field experiment, maybe they're going a little crazy, so we checked it against chamber results. And so here we're showing a comparison of alpha pinene versus beta pinene with consistent chemistry. And again, here we have in the shaded part is the percentage distinct. So with the different precursors, 85% of things were different at the molecular level. And then doing the same precursor, but now slightly different fate of the RO2 radical, we see that 63% are distinct. So a little bit more agreement here when we're comparing the different radical or same precursor with different chemistry fates versus different precursor. And we also have a couple of other experiments. Oh, I should show here. These are overlapping compounds shown on the log-log axis. And so both precursor structure and the oxidation pathways produce this compositional variability. And the other things that show this are also similar. Like this, we're doing HO2 oxidation with alpha pinene versus beta pinene, and then beta pinene doing the same thing with the NO3 versus HO2 RO2 radical fate. And so we observe this in the chamber as well. Finally, we went and used the Gecko-A chemically explicit model and generated very large mechanisms that were isomer specific for all these different 4 experiments that we did in the chamber, and they also ran one under the forested conditions. So you can see here on the left is the gas phase results, on the right is the particle phase results with the percentage of compounds that distinct being on the left axis, and then the reaction time as we proceed left to right. And so here is where we have the same precursors at the bottom. So we start, and then different precursors at the top. And so if you start with the same precursor, things are more like when you begin, and then they diverge from each other. And if you start with different precursors, they get a little bit more similar as they age into gas, as well as the particle phase. So we're able to replicate this and show that there is indeed a high amount of variability that's observed in the atmosphere, replicated by the Gecko-A model, which is a very large mechanism. So we also did a sensitivity analysis to make sure we weren't fooling ourselves with our limit of detection. And so we varied our limit of detection both in our results from the 3 field sites, the chamber, as well as the gas and particle phase results in the model. And you can see we don't see much deviation from our results here as we increase and decrease our limit of detection. And then we were able to extend this analysis with the model results since we could push further, and we do see a little bit more of an effect when we push further, but still this is only -6 to +4%. It's the maximum variance that we're able to create by just shifting our limit of detection. So why hasn't this result been, takeaway, no, our results were not biased by the limit of detection. So why might this have been seen in some previous studies? So working with our co-authors, we compared our results in this study to some ultra-high resolution mass spec results, the model results, as well as sort of standard sim study. And so here we're looking at how close the 2 formulas occur to each other in terms of their difference in mass. Versus the MS resolution of each compound to the nearest compound. And so what I'm showing here in this dotted line is actually the SIM's capability to resolve and assign formulas. And so if you're to the left of this line, you're in a more difficult regime to actually differentiate 2 compounds that have very similar molecular masses. And then if you're to the right of this, it's more possible. And this, we worked on this with some very good SIMS operators from Colorado. So this was a really interesting way to put the results in perspective, that perhaps in similar studies with ultra-high resolution mass spec and also our LC study here in the model, we're actually able to differentiate things that would otherwise be too close to each other in mass and would be observed as the same species in other studies. So we did a few other things, and just to touch on one of them here, we looked at the back trajectories. So we modeled them for each of the 3 sites, and in summary here, we're able to see that we're not able to explain the percentage uniqueness or distinctness by the back trajectory, but we do see that when things have very unique back trajectories, so all the way up here in the top right corner, we do have sort of very unique mixtures of our functionalized OA. We compared this against RH and T and also to the AMS results and see no significant correlation between any of those and the percentage that's unique. So in summary, these molecular level results demonstrate a greater level of compositional variability that is typically observed in less speciated measurements. And we observed this at 3 different sites in chamber experiments and with completely independent chemically explicit modeling. And so we see here really a complex interplay between precursor emissions, the chemical oxidation conditions, and the air parcel history that together are going to provide this molecular level variance. So it's not just one of those factors, and where you have multiple shifts in one or more factors, you can then even affect it more because you're playing with more variables. Finally, so this is interesting for us to think about as we're looking at bulk organic aerosol metrics from field campaigns or chamber studies. So we may actually be collapsing variability in composition. When we think it should be more similar, it may in fact not be at the molecular level. So there's a lot of opportunities to garner valuable information from these kinds of studies and use it to advance our understanding strategically. So I'm not advocating with this that we need to go out and do a molecular level, untargeted analysis and understand every single compound in every single sample for each of our field studies, but we need to think about this as we're developing our SOA metrics and our parameterizations for models, and not always think that something is the same just because that's the same O to C ratio. And so this variability is going to potentially lead to variability in chemical physical properties and their ultimate impacts. There's a number of different properties that have been observed to be sensitive to this in the literature. And put a quick little bonus in here. We, in our follow-up paper to this, looked at viscosity and miscibility. And see here that if we're looking at Atlanta summer and winter, that this variability in the organic aerosol composition has some effect on mixture-wide phase state. And so you can see that here with the, this is just the dry aerosol. And then as you're adding organic aerosol, liquid water, and then the inorganics, you can see that we do sometimes shift into a semi-solid regime during the summer, and in the winter we do go back and forth here between semi-solid and liquid, but there are really other important factors that are driving this as well. Sulfate and ammonium concentrations and RH in total aerosol liquid water. So while this is causing some effect, this changes molecular variability, phase state is still largely dominated by these other factors. And so here's a summary from the different field sites where we have 2 scenarios here. If it were well mixed, it would be the solid boxes here, here, and here, and then if we actually have a phase separated system, the organic subset of that phase separated system is going to be sort of in a mix between the liquid regime and semi-solid regime between those different samples. And so, those are the phase separated scenarios. So we extend this to miscibility, and so first I'll point to this figure on the right. We were looking at for Atlanta both summer and winter mixing of the organic fraction with either inorganic aerosol liquid water, isoprene products, or monoterpene oxidation products. And so you can see in the summer here we actually, and we see the same result in the winter, we have unfavorable mixing conditions with inorganic aerosol liquid water, which leads us to believe that these are mostly phase separated between the organic fraction and the inorganic aerosol liquid water. And then for monoterpene products, we are always have favorable mixing, and then isoprene products, just for some of the methyl tetrols, some of the time we have unfavorable conditions. And so when we combine the results for Atlanta summer and winter, we're looking at both the phase state shown here on the x-axis, and then with this solubility factor, we can see that, again, for these particles that are phase separated, the organic fraction is often going to be well mixed in the summer, but in the winter, we will get into a situation where kinetically limited due to the semi-solid nature of the organic fraction in these particles. And so we were able to take the results that we had initially and then show here for the viscosity and phase state and the miscibility how those complex mixtures will behave in the atmosphere for these factors. And one of the things that I'm very interested in because of how molecular structure is so critical is the effect on ROS formation endogenically. So with that, I will stop, and if there are any questions, I'm happy to